Who sent me a Slack?
Hey. Hello, everyone. Welcome to the second talk this term. Aaron's going to talk about Python. And so, as usual, we do these talks pretty much every week at this point. And yeah, welcome to Aaron.
Okay, hello. Thank you very much, Charlotte. So, my talk is about what Python's really doing when it runs your code. So, the computer doesn't directly understand the Python code that you write. There needs to be an interpreter in the middle. It would be very nice if computers could magically understand your Python code with no interpretation required. I have emailed many processor manufacturers to ask them to include the magical computer snake that understands Python. Intel have stopped replying to my emails. I don't know what I'm doing wrong. There are quite a lot of Python interpreters available for different use cases. The one that you probably use is CPython, which is implemented in C. This is the sort of general purpose reference implementation. Other interpreters will differ, but I'll be talking about the CPython interpreter in particular. There are two particular areas of that interpreter that we'll be covering in this talk. We'll be looking at the very low-level elements, like parsing your code and converting it into bytecode. If you aren't familiar with those terms, then hopefully at the end of this talk you will be. And there's also the very high-level element of classes and instances of those classes. There's a lot of glue holding these together in the forms of implementation of integers and functions, but quite frankly, that's just not as interesting as these high-level and low-level parts, so we'll be glossing over that for this talk. So the first part of this low-level understanding is tokenization, which is the process of breaking down your string of text into its smallest elements, which we call tokens. Working with these tokens is much easier than working with a big string of text. It makes everything in the future quite a bit easier. Let's take an example Python program that we'll be using through pretty much the whole talk. So this simply goes through the numbers 0 to 9 and prints them out. So it prints number 0, number 1, number 2, etc., all the way up to number 9. You'll also notice that I've shown two areas of white space here. The enter character, or the return character at the end, and the indentation. Obviously in Python, indentation is important, and in this case, so is the new line. So the tokenization process pulls apart this string of text, and then categorizes each of its logical elements, its tokens. So you can see here, starting from the top left, that for, I, in, and range are all categorized as names. For isn't technically a name, nor is in. They are keywords, really. But Python isn't concerned with that yet. We'll only deal with that later. For now, everything's a name. The other advantage of doing this tokenization process is that it removes unnecessary white space. It wouldn't matter with the result of the tokenization if we had brackets around, white space around the brackets in our range call or anything like that. It's all removed here. Makes everything a bit easier to deal with. And once again, here, in our tokenized representation, there are also tokens for the new line character and the indentation character. They are both important elements of Python, especially indentation. If you'd like to write your own Python code and see what it tokenizes to, it's really easy to do that because there's the tokenize module built in. Simply do on your terminal python 3-m tokenize for module tokenize, pass in a file, and it gives you the tokens. That -e makes it a bit easier to work with. Without that, it'll show all symbols as just a symbol. Makes everything a bit easier to read. Once we've tokenized, we can parse our code, which constructs an abstract syntax tree for it. This adds a bit of two-dimensional structure to how Python actually understands this code. So let's take a simpler string of tokens this time. This is just doing 3 plus 2 times 5. Now, we all know that multiplication happens first. 2 times 5 should happen before the 3 plus. But the tokenized representation of the code doesn't actually tell us that. It's just a flat list of tokens. Parsing will take this and put it into a nice tree that we can work with. So let's go through what this tree might mean. So at the top we have expa for expression, because 3 plus 2 times 5 is all an expression. There's one child of that, binop for binary operation, and its children are 3, that's one side of it, add, and another binary operation. That binary operation is 2 times 5. You'll also notice something interesting about constructing an abstract syntax tree is it gives a bit more meaning to some of the tokens. In our tokenized representation, the plus character and star character are just called plus and star. It doesn't express the semantics of them. In our tree, they are add and mult for multiply. So it's adding more semantics in. Now, we can actually sort of start to execute our code off this representation by going through this tree depth first. So if you went to the very bottom layer of the tree, you execute 2 times 5, which yields 10, then 3 plus the result of that, you get 13. So we can actually use this to build our own sort of primitive interpreter, just by going through it depth first like that. And there are some popular interpreted languages that do this, mainly scripting languages that are quite similar to Python, like Perl and Ruby before version 1.9, both did this. But there is an issue with it, and that's that it's really slow. Computers don't map to this sort of representation as well as they do for something flat. Memory addresses are an integer, not coordinates or a path down a tree. Computers will work better with something linear. So what if we could convert this representation and the semantics that are associated with it into something linear? Well, Python does this using bytecode. So bytecode is a flat representation of the behavior of your program. If you're familiar with machine code, it's quite similar to that. While machine code is the native language of your processor, Python bytecode is the native representation to the Python interpreter itself. If you've ever written large Python projects, you've probably noticed PyCache directories popping up, and in them PyC files. These are cached bytecode generated for your Python source code. Let's take a few files here. At the top we've got example.py, which contains that for loop with a print statement in it from earlier. And then we've also got a main.py file, which just imports that file. The reason I've structured it like this with an import is because by default, Python won't cache bytecode for the file you're running, presumably because it changes a lot. It'll only generate bytecode for the files that you're importing and cache it. So in our PyCache directory there, we have that cached bytecode for our example file. Let's have a closer look at that now. So this is a hexadecimal representation of the bytecode within that file. I don't know about you, but I'd much rather work with the source code on the right than the representation on the left. I cannot read that. Don't think any human would want to be honest. Let's go through that structure anyway so we can see how it works. It starts with a header. In this header, you have some information about the bytecode file itself. The first chunk of it is a magic number. So this includes information about the version of Python that generated this bytecode. This is so that you don't accidentally run, say, cached bytecode generated by Python 2 in your Python 3 interpreter. It's very unlikely that it'll work. You also have the modification date and the size of the source file that generated it. So you can compare this against the source file this cached bytecode came from. If it's different, you need to regenerate this cached bytecode. If it's the same, you can just use this cached bytecode. Now, what about the rest of the file? The rest of it is called a marshaled code object. So marshalling is a way in Python that you can serialize an object, which effectively means converting it to a series of bytes, usually so that you can save it to a file or load it from a file, sometimes also so you can transmit it over a network. So you can marshal any Python object. You can marshal a dictionary, marshal a list, marshal an instance of a class. Most things can just be marshaled and saved and loaded. Here, we're not marshalling just a list or a dictionary, though. We're marshalling an actual code object with our bytecode instructions inside. Python is so object-oriented to its core that even the bytecode it uses to execute is effectively an object. So inside this code object are our real bytecode instructions. We still can't read them like this, but fortunately there's a module built into the Python interpreter called dis, for disassembly, which will show them in a much prettier manner. There it is. So, you can see it's broken down into two main sections here. There's a top section, which is our first line, and the bottom one is our second line. They're both numbered to correspond with the source code. There's the source code from earlier, so you can see how they compare. Now, down the middle here is the most important part, which is the opcodes. These things like setup loop, load name, load const, call function, etc. We'll get into more detail about what each of those does in a minute, but as a general rule, they have one reasonably simple instruction that they do that's quite generic and reusable. They're similar to an assembly language if you've written in an assembly language before, but for the Python interpreter itself. Let's go through how this actually executes the code we wrote earlier with the help of a stack. I've hidden some of the unnecessary stuff there. So, first of all, our first instruction, set up a loop. This tells Python we're about to start a loop, get ready. This also means that if you break from your loop, it knows where to go. See on the right in the operand there, we say to 28. That means that byte 28 is the end of the loop. Well, one after the end of the loop, technically. If we break from our loop, that's the byte we go to carry on executing. The next instruction is load name. So these load instructions all generally take something from our outer environment or from the bytecode itself and put it onto the stack. So load name range will take the range, the reference to the range function, and pop it on the top of the stack. Next we have load const 10, which as you can suggest, as the name suggests, loads the constant 10 onto the stack. By the way, these numbers before range and 10, they're references to the individual items within the code object. There's quite a lot of complicated internal workings to how it actually finds these names, but essentially only the names it's going to need are cached inside the code object, so it can just pull them straight out with an index, in effect. Call function. So the 1 means it takes one argument. And if you remember our source code from earlier, what's on the stack might be looking quite familiar now. We've got range and we've got 10. So we can call range 10. And when this is evaluated, it'll put its return value onto the stack, which is an iterable. So this is a range iterable in particular. An iterable is something which can, when Python asks it to, become an iterator. And an iterator produces values until it runs out. Now, the reason we do this rather than simply generate a big list is because, say you wanted to have range 1,000,000, you don't suddenly want 1,000,000 integers in your memory. If we use an iterator like this, it'll just generate values as it needs them until it runs out. This getIterator function, as I just described, takes an iterable and converts it into an iterator. Now that it's the iterator, it's got a next value that it'll go to when we next ask it for one. So it's a range from 0 to 9, and the next one, the next value we pull out of it will be 0. For-iter. This is the main instruction that implements the behavior of a for loop. This will take one value out of the iterator that's currently on the top of the stack and put it at the top of the stack. So the next value that will come out of our range is 0, so it pulls a 0 out, pops it on the top. And as you would expect, the iterator's next value has changed to 1. So when we next pull something out, it will become 1. This 0 then needs a name. It's used in a for loop, so we need to give it a name so we can reference it later. So this will bind the name I to 0. Load name, again, loads the name print onto the stack. Load const loads the string number here onto the stack. And load name I, well, we've just assigned to I, so we can pull that value out, put it on top of the stack as well. Call function 2, calls a function, 2 arguments. Looks familiar, we want to print number 0, that would get printed, and it puts the return value on the top of the stack. Print doesn't have anything useful to return, but every function in Python has to return something, so it just returns none. We don't actually care about that value, so pop top instruction will just discard it. Finally, implementing some sort of looping structure, jump absolute will take us back to byte 10 of our bytecode. So we go straight back up to the top. And there's our for-iter again. So this just keeps looping now. So for-iter runs again, pulls one value out of the iterator, puts it on the top of the stack. It's 1 now. You want to store that into the name I, so it gets stored there. Then it would load name print, and you get the idea. It's going to keep doing this, 0 to 9. But what about when the iterator is exhausted, when it runs out of values? The for-iter instruction there has an operand, which means 226. So when it's finished, it'll go to instruction, well, byte 26 in our bytecode. and it'll run these. Pop block says, this loop's done. If we break now, not my problem, it's the block-up's problem now. This loop's finished. Load const and return value will load none onto the stack and return it. So that's the whole bytecode of that for I in range 10 print number I. This is what's internally being run when you run that code. But how do we make this fast? It turns out optimizing a dynamic language is actually really hard, because with a dynamic language there are behaviors that could occur that you don't know about. Now, one of the optimization steps that CPython actually took is to use bytecode in the first place, because it's a fair bit faster than a tree representation like some other interpreted languages use. But that does have some other optimizations as well that can speed things up a little bit. By default, the interpreter will attempt to predict the instruction that's going to come up next while it's running bytecode. So say that you load a name onto the stack. Chances are your next instruction is also going to be load a name, because you're probably setting up for a big function call, or any size function call really, or just loading lots of values onto the stack. So Python will predict, I think the next instruction will be a load name. If it gets it right, after the current instruction, it can simply jump straight to that instruction's handler without doing an entire loop of its whole interpreter process again. This shaves mere clock cycles off your processor's running of the Python interpreter, but it can all add up if it gets those instructions predictions correct. And you know it's fast because it uses gotos in C. Another thing that you have is the -00 flag, or optimization level 2. This is if you really need the most speed that you can get out of Python's interpreter, the CPython interpreter. So this will remove any assertions you have, remove any if debug statements that should only run if you're debugging, and even remove any doc strings so that your Python interpreter doesn't actually need to evaluate them. You're really getting the most out of your interpreter there. What if that's still just not enough? What if you need even more than that? Well, there are other interpreters available that unfortunately I don't have time to go into detail about today, but can speed things up a fair bit. So the PyPy interpreter will actually compile parts of your Python code into real machine code that your processor natively understands, so that you can run at pretty much maximum speed for that Python code. That can lead to massive performance improvements and is a really great step if you need the absolute fastest you can get. Although if you need the absolute fastest you can get, why did you write a project in Python? That concludes the lower level look at my talk. But let's move on to something a little bit higher level now. So classes. So Python classes are actually a lot simpler than they might seem. A lot of the underlying logic behind your Python classes and their instances are actually just one big dictionary. Let's have a look at how that might work. So here's a super simple class, animal. It has one function, which is its initializer, which sets a given parameter as an attribute on that function called name. So say I wanted to create mog, our animal, we can do animal mog as a string, and then that will create an instance of our class mog with one attribute, which is name. We could do mog.name, and it would return the string mog with a capitalized M. But where's it actually putting these attributes? Turns out it's nothing complicated. It's just a simple dictionary that's hidden behind this magic attribute. Magic meaning it's got 2 underscores to the side of its name. Here, these are all the attributes we've assigned. We've only assigned one, it's the name, and its value is mog. Simple dictionary. When you do mog.name, all that's really happening in the background is that Python's retrieving this dictionary and looking up the name key. There are some exceptions to this rule. If you've defined fancy classes using the descriptor protocol, then it'll execute some extra functions to make a bit of magic happen. But for the most part, this is all that's really going on when you access an attribute. There are some other underlying dictionaries, but this dict is by far the most used. Let's make our example a little more complicated by adding a second class that inherits from the first one. We've added a cat class now, which inherits from animal. It adds a method called meow, which will print the cat's name says meow. So for our mog cat, it would print mog says meow. If we instantiate mog again, but as a cat, look at its dictionary, it's, as you might expect, exactly the same. But there's a meow method now, and if we call that, it will work. But where is it? It's not on this instance, because most of the stuff we care about in the instance is stored in that dictionary. It's not a key in there. Where is it? Well, it turns out that the underlying structure of a class is also a dictionary. There we are. It's a slightly confusing looking dictionary, but it's still a dictionary. Technically, it's a mapping proxy, which is sort of an internally optimized version of a dictionary. 3 things here. Module main simply means it was defined in the main module. Meow, there's our function. And doc would be the doc string of the cat class if it had one. So when we want to call this meow method, it'll find it in cat instead of our instance and pull it from there and call it. Again, where's that initializer though? We haven't declared another initializer in cat. It's just using animals because we've inherited from it. But this dictionary doesn't have any reference to animal. Well, let's have a look at animal first. Animals dictionary, among some other stuff which I've omitted, does have that initializer. So we can construct new instances of animal. But how does it find it? Again, there's no reference from cat to animal in its dictionary. Well, there's one more key component of Python classes. They have something called an MRO, or Method Resolution Order, which is a list that you can access through a quick method call on that class, and it returns the order in which it will look for methods on that class. So when we call cat.mro, the first item is cat, because a class will always check itself for its methods first. Then it'll keep looking up the chain, so the next one is animal, and the next one is object, because classes will implicitly inherit from object. So that's how, when we instantiate cat, it's finding items in animal, like the constructor. Let's reel our example back a bit, though, to show one last thing. So it feels like, if you are aware of time complexities and speed of different operations, using a dictionary feels a little bit wasteful for some of these tasks. Just for that simple class with one attribute, what's the point of going through a whole dictionary lookup and dictionary creation when there's a lot of overhead to that? We have to calculate keys and do hashing and all complicated, scary stuff. What if we could just say what attributes our class is going to have from the get-go? Well, Python does offer a facility to do this called slots. If you define slots for a class, it tells Python, we're only going to have these attributes, don't need to consider any others, don't bother making me a dictionary, we'll just use these, it'll be fine. Just statically allocate these. Now, accessing any other attribute will cause an attribute error. The only one you can use is name now. So with this method, everything's a bit more memory efficient and perhaps even a bit faster, because you don't need to have the overhead of a dictionary. Finally, the great thing I really like about this topic is that in many cases you don't need to jump straight to documentation or Stack Overflow or a man page or anything like that to find out how it works. Just write a quick experiment yourself, poke the language using the techniques you already know, figure it out. So let's have a quick look how easy it is to really find out how Python might implement something. Do a super quick demo with super simple multiple inheritance. So I'll open a terminal here. Is that big enough? Cool. So I'd like to see, how does Python's MRO react if we declare a class that inherits from more than one other class? Well, let's write a super quick example class that just doesn't do anything, and another one, and then one more class that inherits from both of them. What I want to know is, does the MRO behave any differently? Does it have some sort of special case where it'll put a tuple in the MRO? What happens? Super easy to figure out, just ask for the MRO. And there we can see. So it starts by looking at itself, as you'd expect, then it will look in A, then B, then object. So the order in which it looks is the order that you specify. If we'd swapped B and A, it would look the other way around. It's really that easy to find these sorts of things out for yourself and see just how that niche feature that you care about might have been implemented and how you can use that in your code. So that's everything. Thank you very much. The slides are available there if you'd like another look at them at some point. Thank you very much.
Right, so thanks. Now we'll have any questions if anyone has any.
I wasn't aware that doc strings were actually extracted by the interpreter of the whichever part, the parser. Is that which doc strings are they? And is it just the text, or does it do any further understanding of that?
My understanding is that it just takes the string that you specify out and sticks it in that class dictionary. I don't know if it looks anywhere else. That'd be something that'd be interesting to look at, actually. But if you want to write some horrendously hacky code that is dependent on doc strings, then go ahead. Please don't, but you can.
So it has to be a string and not a comment.
That'd be interesting to look at, actually. Given that it needs to be a Python object so it can put it in that dictionary, I'd imagine it wants it to be a string, but if it can convert that, that'd be interesting to look at. Again, using the techniques I've shown you, it's quite easy to go and find out.
Thank you.
So with the slots thing,
Yeah.
what I'm curious about is, do you know if it uses like static? So if it looks in the parsing phase at the name and then generates an array offset or list offset even to generate that in like lookup for that variable.
If that were to happen, I doubt it would happen as early as parsing. Parsing isn't too concerned with semantics quite that deep. Although at a later stage, although I'm not 100% sure on the implementation, I would think it'd be something quite like that. Yeah.
Okay.
Is the Python bytecode portable between similar versions of the Python interpreter?
Portable, if the magic number is the same, you'll be fine.
Okay.
If it's not worth trying. It might work, but it's a real risk. The idea of that magic number is that if it's the same as the one your interpreter is expecting, it should work.
Okay, and is the Python bytecode is that a feature of Python, or is that a feature of CPython?
From what I've read, I think it's more of an implementation detail of CPython. Yeah.
Okay. And so the last question,
Sorry?
is it standardized enough that you could make a Python interpreter for a different, so just the very lower half of that for potentially a different platform?
It is quite well documented, so you presumably could do that, I would imagine, yeah, if you wanted to.
Okay.
Well, if that's everything, then thank you all for coming, and I believe that we'll be heading to Glass House for a drink if people want to come with. And yeah, next week's talk is by Jacob. It's going to be on Altazar and how terrifying it is. And yes, we'd be happy to see you there.